Hello, students. This is the Sensation and Perception Review to get you ready for the test. It will be coming up next week, and there will be 33 multiple choice. That was my error. 33 multiple choice. 3 of those will be from old chapters, straight word for word from old chapters. One of them will be an AAQ, which you're very familiar with, the 6-part AAQ. I'll give you a little bit of heads up when we get to that part. So let's start talking. Selective attention. This is a conscious awareness of a stimulus that determines what sensations we perceive. So we take in all of these sensations, but we can't actually perceive it all. Our brain just can't pay attention to all of it. And in fact, here's your first little clue. A lot of the AAQ is about this selective attention of what your brain can actually pay attention to and perceive. Inattentional blindness is the failure to perceive a stimulus when attention is redirected. Do you remember when I showed you the video of the moonwalking bear? When you are forced to direct your attention to something else, other stimuli are going to be missed. Whether it's something that you don't see, whether it's something you don't feel, whatever it might be, that's called inattentional blindness. The cocktail party effect is our ability to detect your name above many voices or stimuli, and that's just how it sounds. The cocktail party effect basically says we perk up, we listen more carefully when we think our name is being spoken. The Stroop test, this is that concussion protocol. Remember when we did the Stroop test that day in class? This is how processing speed is slowed by competing stimuli. There's an interference in cognition, and that interference happens in our perception, in our ability to perceive what's happening. But it's really about that processing speed. It really slows down when you have to think about the word that you're going to say, which is actually a different color than what the word is listed, for instance. Sensory adaptation. This is a gradual desensitivity to a constant stimulus. This happens in the brain. So we talked about, going nose blind in the locker room, or you don't really smell your house or whatever it might be. You don't feel your mouth guard, maybe. This is a gradual desensitivity. Now you're still getting those sensory receptors. You just don't perceive it in your brain the same way you had maybe done right away when it first kind of came at you, if you will. Habituation. This is a decreased behavioral, you should probably underline that word behavioral, a decreased behavioral response as a result of sensory adaptation. So when we have this constant stimuli being thrown at us, if you will, we stop responding. And so let's say, I think smell is one of the easiest ones. Let's say we smell something really bad and it's just really, really strong. We might even do something like plugging our nose, and then eventually we kind of quit plugging our nose because we've actually become adapted to the smell. So the habituation happens in the body. It's a behavioral response. Let's talk about the eye. I want you to know a couple parts in particular, and of course the most important part is the retina. The retina is the inner surface of the eye. It begins the process of transduction. This is where these receptor cells, such as bipolar and ganglion cells, are located. And it's in the retina where these receptor cells are detected and concentrated. We find very, very specific cells in the retina that we don't find really in any format, in any other manner, anywhere in the body, including things like rods and cones, which we'll talk about here in a second. The fovea, this is the center of the retina where cones are concentrated for fine detail. This is where we have what we call our greatest acuity. You can see the best, like the most clear vision that you have is coming from your fovea, but that's a very small part. If you remember that eye diagram, it wouldn't hurt to take a look at that. It's at kind of the back of the retina. Is the fovea. Rods, those are those special receptors for black and white vision. We have, I don't know, like 5 times as many rods as we do cones, many, many, many more rods, because we need to be able, evolutionarily speaking, we need to be able to see darks, shadows, things, are much more important than seeing in color. Cones are for color vision. There are fewer receptors, exactly for what I said, the reason, evolutionary wise, we don't need to see color. Today we do, but maybe not 20,000 years ago. All right, so let's get into the just noticeable difference. This is the minimum amount of stimulus intensity that must be changed in order to produce a noticeable difference. So you have to meet the absolute threshold, and we'll talk about that here just in a moment. So the just noticeable difference is the amount that you have to hit that level, that threshold, if you will, in order to notice a difference. It's called the difference threshold. Weber's law works on the just noticeable difference. It's the just noticeable difference of a stimulus is a constant percentage or proportion. So Weber's law says how much is added or subtracted, for that matter, to detect a difference is going to be the same no matter what we're talking about, but it's going to be proportion-wise, not amount-wise. Like we talked about 1 teaspoon. Well, adding 1 teaspoon of sugar to a cup of tea, you're probably going to tell a difference. Adding 1 teaspoon to a gallon of tea, 1 teaspoon of sugar to a gallon of tea, you're probably not going to be able to tell a difference. The JND is based on a percentage or a proportion. The absolute threshold, this is the lowest intensity of a stimulus that can be detected 50% of the time. So at the lowest point, where can you detect that stimulus? Where is that threshold at? The trichromatic theory. This is the Young-Helmholtz theory. I think I referred to it as the Young-Helmholtz in your test, so make sure that you know this is the Young-Helmholtz theory, that the retina contains 3 basic photoreceptors, red, green, and blue. And those photoreceptors are basically what produce all the hues and colors that we are able to perceive with our brain. So all these colors basically in the retina, these red, green, and blue cones, allow us to see many, many different shades, many hues of color. The opponent process theory. This is the most useful theory for explaining color vision and after images. We did that lab that day where we stared at that little square, and then we shifted our gaze and you saw something different appear. That's known as the after image. What color comes after you've fatigued your photoreceptors? So it's most useful for explaining color vision and the after images that continue to travel to the visual cortex after the fatigue of photoreceptors. The gate control theory. This is kind of the second part of the AAQ, understanding pain, how pain is perceived through the spinal cord, either blocking signals or opening them to allow sensation to be perceived in the brain. Now, some people have a high tolerance for pain, some people have a lower tolerance for pain, but either way, we all need to experience pain, we need to perceive pain. But if you remember, when we talk about selective attention, sometimes some pain gets blocked out. When we talk about the gate control theory, minor pain can be blocked out pretty quickly. Endorphins kick in and your pain is eased pretty quickly. If it's major pain, it might take a little bit longer. But we can't pay attention to a whole bunch of things all at once when we're perceiving sensation, including pain. The vestibular sense. This is our ability to sense balance and equilibrium, how we don't feel like we're woozy or gonna fall over, from feedback about our head position. And our vestibular sense all comes from feedback information we get in our inner ear called the semicircular canals. If you have that if you have that diagram of the ear, the semicircular canals are those ones that look kind of like little pretzel shapes in our ear. The kinesthetic sense is our ability to sense body position and movement of body parts through receptors in muscles, joints, and tendons. The kinesthetic sense is all how we move. I think sports players, more than anybody, gymnasts definitely understand the kinesthetic sense. Think about, timing to go up for a spike, or timing for a baseball, for a swing, going up for a blocked shot, whatever it might be. It's how we can sense the position of our limbs and our body through those receptors. Top-down processing. This is used for context. We use top-down processing to use contextual information that's aided by culture or expectation. So we take the context of something, and then basically we understand it based on maybe something we have already know, what we expect to see, something that we know is true of our society or our culture. And so we use all that contextual information. So when I showed you those pictures of baby pictures, you didn't have a lot of context. You were actually using bottom up because you didn't have hardly any context to go on. You couldn't tell if it was a girl or a boy. Then I told you it was a teacher, and that gave you a little bit more context, but you were still kind of you weren't doing a whole lot of top-down processing. You're doing some more, but you're still doing a lot of bottom-up processing. So you're aided by this context. In the ear, the sound waves travel through the outer, middle, and inner ear, and it's in the inner ear that everything happens, but these sound waves have to kind of travel down the ear canal through those little bones. And let's talk about those. The ossicles are those three little bones, the hammer, anvil, and stirrup. Notice I have like an arrow to each of them. The hammer stimulates the anvil stimulates the stirrup, and these are the three little bones in the middle ear that transmit the sound as vibrations to the cochlea. So the sound waves travel down the ear canal, and then it's this vibration that actually triggers vibrations in the cochlea, and it's the stirrup, actually. That's the last one that almost touches, if you will, the cochlea. So the cochlea is a primary organ for hearing. It's that coiled, bony, fluid-filled structure where the nerve impulses are transducted. Like in the eye, transduction happens in the cochlea. This is where it's happening here in the ear, and it's changed from simple sound waves and vibrations into a neural impulse. Let's talk about hearing loss. Conduction hearing loss is when there's damage to those little bones. It's less serious, probably actually less common. The more serious one is sensory neural hearing loss. This is damage to the receptors in the cochlea due to especially exposure to loud noises, anything over 85 decibels, aging, heredity. Those are all factors that could contribute to sensory neural hearing loss. The pitch theory. Now this is all happening in the cochlea. The cochlea basically is, of course, where transduction happens, but we know that the frequency theory is how we understand low-pitched sounds. The frequency theory bases its theory on the rate of impulses, that it matches the frequency of a tone, the length, if you will, the wave length of a tone. The place theory is also called the Helmholtz theory. We've already talked about Helmholtz. He had his hand in sight and sound. The place theory is how we understand high-pitched sounds. These are from vibrations in the cochlea, which are triggered at different places. So remember, if it's closer to the base of the cochlea or to the apex of the cochlea, determines its pitch. And if it's at the base of the cochlea, it's a higher pitch. And remember those little hairs in the cochlea, they're triggered by the basilar membrane, that movement. And so if they're triggered at the base, then that movement will help us perceive a high-pitched sound. Sound localization. This is when we perceive sound based on which ear collects the waves first. However, it's very difficult to distinguish above or directly behind us because the sound isn't hitting one ear or the other at like sooner, and so it's really kind of hard to tell where exactly it is. My helpers who helped me out with this little experiment did a good job, because typically when I clicked above their head, they couldn't distinguish that it was above their head. They usually said it was behind them. Perceptual constancy. This is our perceptual understanding of objects despite change. So we see something, for instance, but our brain says, well, you're not actually seeing what you're looking at, because if you were, things would be completely distorted. Like what you saw going, way far away would look tiny, and you know that what you're actually looking at isn't shrinking or growing. So we talk about size constancy. Things don't shrink or grow. Shape constancy. They don't change their shape just because the angle that it's hitting our retina is different. If something is in a shadow, we know the color doesn't change. Now, what we see on our eyes is not actually what our brain perceives. So if you've ever heard the expression, our brains can play tricks on us, our minds can play tricks on us, it's a good thing, actually. We would like some perceptual constancy. Depth perception. We perceive objects in 3D, but they're presented on our retinas in 2D. So this allows us to judge distance, also speed as well. It's very good that we have the ability to judge distance, because it's basically helped us evolve as people. Some animals have really great depth perception. Some animals don't have very good depth perception. Humans have good depth perception. Actually, men have better depth perception. If you think about it evolutionary wise, men need to have better depth perception, because they need to judge basically problems. They need to judge if there could be as I always say, if there could be somebody coming into your cave and clubbing you over the back of the head, you got to figure out how far they are away. Women's actual depth perception is not as good. Having said that humans have depth perception, it's a good thing. We even know that infants have an innate ability to judge depth. It's called the visual cliff. They did that experiment. I'm not even going to call it an experiment, but they did a test, I guess, if you will, on babies to see if they would cross that platform, and they wouldn't, because they think that they would get hurt. It's called the visual cliff. Binocular depth cues, this is all part of our depth perception. This is the ability of two eyes to basically calculate depth in a wide scope. It's much easier when we threw those balls in the hallway. It's much easier to calculate depth when you have two eyes rather than one. And so those who are maybe have an eye infection, or you've had a serious problem with your eye, like that would lead to blindness, it's much harder to judge depth. One binocular depth cue is called retinal disparity. We perceive depth by comparing two images on the retinas and then computing that distance. And so if you only had the ability to do that with one eye, we don't compare it to anything else, right? Like we have these two images hitting our retinas, we compare how far it is by comparing these two images. Our brain computes that very, very quickly. And finally, Gestalt. Gestalt is integrating pieces into a meaningful whole. We'll talk about this many other times in psychology, but I want you to understand that Gestalt is, and the meaningful is important. Looking at the parts is good, but putting it into a larger understanding of the whole is even better. So oftentimes we look at figure, we look at ground. That's the most common, the figure ground Gestalt. There are many examples that I had put on the PowerPoint. We looked at those in our book together, but integrating them into a meaningful whole is what we call Gestalt psychology. Okay, so that's it. If you have any questions, of course, please feel free to reach out, but I hope you are ready. Talk to you soon. Bye-bye.